Hello everyone, my name is Goran Žužić and this is a long version of the talk titled An Overview of Universal Optimality in Distributed Computing. The shorter version of the talk I will soon give in ADGA 2021. So let's start. So the setting is that we are given a distributed network G, and when I say a distributed network, you should have in your mind an undirected graph, such as the one shown on the right. So, your task is to solve a global problem on the network graph, such as the minimum spanning tree, abbreviated often as MST, single source shortest path, mincut, etc. So, when I say a global problem, I want to specifically exclude problems that you can solve only by looking locally around the graph, such as the coloring problems, or the maximal independent set type of problems that you can solve by only locally looking around the graph. On the other hand, problems like the minimum spanning tree, if there are two nodes that are very far away, they kind of need to talk to each other, otherwise you cannot really figure out is it even possible to make any spanning tree connecting the nodes or not. So by global problems, I won't give any explicit definitions, but you can think of the minimum spanning tree as an example. And just the idea is that every two nodes needs to hear at least something from each other in order to solve the problem at hand. So the goal that you should keep in mind throughout this talk is that we want to design a distributed minimum spanning tree protocol that is as fast as possible on our network graph G. Alright, so now the input to the minimum spanning tree problem, what is that? Well, you can imagine that each edge has a renting cost. So how much do we need to pay to rent it? And the question is, we want to find the tree of minimum cost that connects all the nodes. And we want to do this in the distributed setting. Now, why do I even focus on, I will mostly focus on the MST in this talk. And why is this okay? Well, keep in mind that this is one of the oldest distributed problems. In fact, it is one of the started the field of principles of distributed computing about 40 years ago in a paper by Gallagher, Humboldt, and Spira in 1983. It is also the easiest hard global problem, meaning that it captures most of the inherent difficulties that arises when you try to solve other global problems. So if you know how to solve MST, everything else will be much easier. In spite of all of this effort that has been actually done in trying to solve the minimum spanning tree problem, there is many important questions that remain. And also the same techniques that I'm going to apply here will actually apply to all the other tasks that I said, the shortest path or the mincut. So just as a first order, you can focus on the MST and the rest will follow. All right. So that's our goal. So what are the challenges that you might already know? So this is a distributed problem, so nobody really knows the entire input. So every node has only a local view. We will formalize this later, but you can imagine that, nobody knows the entire network, but you only know, every computer knows around its neighbors, and the renting costs are only incident to it. And furthermore, we're in the congest model, which means that the messages are small. So we will also formalize it later, but you cannot really send arbitrary long information. You need to be somewhat smart about what you send around. So this is a high-level overview. So now let's formalize our model a little bit more. All right. So we are, as I said, in the so-called congest model, which I'm sure most of you are all familiar with. But I will still define it. So the idea is that the network topology is abstracted as an undirected graph, such as the one shown on the left. So clearly the nodes are computers and the edges are cables connecting those computers. Communication is performed in synchronous rounds. So you have round 1, round 2, and so on. In each one of those rounds, neighbors, so neighboring computers, exchange small messages. By small, here we mean polylogarithmic in size, as denoted by the O tilde of 1 notation. So this is what the O tilde of 1 means. It means it hides polylogarithmic factors. So in every round, you can think of it small, but actually it means you can exchange a polylogarithmic many bits between adjacent computers. Computation in this model is free because this model focuses mostly on the communication costs. And initially, nodes only know their immediate neighborhood. So for instance, this computer like this, just a moment. this computer here, will only know the input and adjacent computers and the input on the adjacent edges. So in the minimum spanning tree, it will know the renting costs of these adjacent edges. Finally, the objective is to minimize the number of rounds until we can solve the problem. So the number of rounds until every node knows the cost of the minimum spanning tree. All right, so this is our high-level introduction that you should keep in mind. But now we're gonna transition on to the central concept of this talk, which is universal optimality. So first, I'm gonna describe with a little bit older and more well-known concept of existential optimality, and then compare it to the new one. All right. So, how do you solve, when you want to solve the distributed minimum spanning tree problem? There is a well-known theorem by Kuten and Pelly from 1998 that says that distributed minimum spanning tree can be solved in O tilde square root n plus d rounds. Here, n represents the number of nodes, and you should think of n as some large factor. Whereas d, is the Hopf diameter, or the diameter of the graph, and you should think of this as a small factor. Mostly because, typically in networks of interest, the diameter is very small, polylogarithmic, because real networks or networks of interest typically have an expander or tree-like structure, meaning that the diameter is very small. Unlike that, and the number of nodes can be huge. All right, so square root n plus d, and that's why the d here is shrinked, so it's a small factor. So think of this as small, think of this as large. Furthermore, there is a theorem by a sequence of papers that says there exists a family of graphs whose diameter can be as small as log n, for which any correct minimum spanning tree protocol requires square root n plus d rounds. In particular, this family is depicted on the left, so it's not that hard to draw. So the question is, all right, so are we actually done? There seems to be an upper bound, there seems to be a lower bound, they seem to match. Now, the problem here is that square root n plus d is optimal only on the pathological worst case graphs. So only on kind of these networks on the left. So this is kind of what we call existential optimality. So it is optimal in the class of, it is optimal in a class of all graphs. So only if you look at all the graphs, you want an algorithm that works in the same runtime in all those graphs. And it doesn't really tell you much if you say, okay, what if I have some special or some nice graph? What if I have a planar graph? What if I have some other, graph with a special property? Can you do anything better? You actually don't really know if you have an algorithm that is existentially optimal, such as this one. Furthermore, existential optimality kind of depends on the parameterization. Square root n plus d is only optimal when you parameterize by n and d. So in particular, you could say, okay, if you parameterize by only n, then there is a very simple order n algorithm. And clearly you cannot do much better, because when you have a path of length n, you need n time for the two endpoint nodes to even hear from each other, so you cannot do anything faster than that. Therefore, you can see that this is a very, let's say, strange way, or not very helpful way of talking about optimality. All right, so this kind of leads to the very natural question: can we do better than this? Can we have an optimality that is more helpful than the existential one? And the answer is yes, and this is a new concept that we introduced in the Stock 2021 paper. And it says the following: well, we say that a single distributed algorithm A for some problem P, such as the minimum spanning tree, is universally optimal if it is as fast as possible up to polylogarithmic factors on each network G that it is being run on. All right, so let's absorb this in a little slower speed. So let's talk this over again. So imagine that you have a single correct algorithm A. You give me a single correct algorithm A. And now this algorithm A, for each network G, and by network just think undirected graph, and for each other correct algorithm B, And this B can depend on G, so it can be specifically constructed in a way that it is as fast as possible on G as it can be. And then it holds that the runtime of A on G is at most the runtime of B of G up to polylogarithmic factors of slack that I allow it for. All right, so this is actually a definition, except I never really told you how you compute the runtime of an algorithm on G. So let's talk about this a little bit more. So the runtime T of an algorithm A of G, of a correct algorithm A of G, is the runtime on the worst case input I. So what is the input in the case of the minimum spanning tree? Well, these are just the edge renting costs, or the edge costs, as I say. So just to keep in mind here we have the definition. The runtime of A and G is just the maximum runtime over all the possible inputs. So just take the worst case input. This makes the definition fully formal, and if you were to read this and internalize it slowly, you should be able to tell me like completely formally what is a universally optimal algorithm. But the thing that you should keep in mind, one that is as fast as possible as any other algorithm on each network G. All right, so let's talk a little bit more about universal optimality, about its consequences and equivalent notions. So the way I like to think about it, that a universally optimal algorithm is an algorithm that perfectly adapts to the underlying network. So it's a single algorithm, you run it on a network and it will use the features of the underlying network in the optimal way. So just to compare it with the previous notion, when you had the existential optimality, like it is optimal in a class of graphs, the new notion, universal optimality, is optimal on each graph in particular. The existential optimality depends on the parametrization. So as I said before, O of square root n plus d is only optimal when you parameterize by n and d jointly. Whereas the universal optimality is optimal with respect to all possible parametrizations because it is parameterized by the graph itself. And this is one way to point you why actually universal optimality is like the property that you want to be striving for. It's much, much, much more stronger than the existential optimality that was mostly the main thing the prior work focused on. So, all right. But still though, it is still a worst case input optimality in the sense that you give me a network, but the adversary still chooses the input. And the other algorithms also need to be able to handle all possible inputs. So the algorithms that you are comparing yourself to. Now you could say, okay, what if I want to be optimal with respect to all the networks and all the inputs? That's a very natural question. However, if you want to do this, there is a very simple argument showing that this is actually impossible. Such a thing I would call instance optimality. And we wrote in our paper that this actually cannot be done by a very, very simple argument. All right. However, let's continue on. I defined the concept of universal optimality, so now let me actually tell you about the recent results concerning them. Alright, so I'm going to spoil it for you. It's actually possible to achieve it. So let's start it this way. There exists a graph parameter called shortcut quality. So for every undirected graph G, there is a graph parameter called shortcut quality of G. It was defined not very recently, so in 2015 by Ghaffari and Hoyper. However, quite recently, in a paper by Hoyper, Weitz, and me, we showed that the problem of distributed verification requires at least shortcut quality of G time. And distributed verification, well, it's a problem. Well, I give you a subgraph of the network. Is it connected or not? Fair enough. So you can notice that distributed verification is a very simple problem, like simpler than the minimum spanning tree and the shortest path or the min cut and so on. So therefore, the same lower bound of shortcut quality also applies for all of these problems. That's interesting in the sense that like shortcut quality, I will define it later, but in the sense it is a combinatorial property of the graph. It's let's say a linear program. You can define it in that way. There are many equivalent definitions. But the point is, it's a combinatorial property. It has very little to do with algorithms. And here, we overbound algorithms by this combinatorial property of the network. All right, so that's the lower bound. And furthermore, we complemented this lower bound with an upper bound that says that you can solve this distributed minimum spanning tree in O tilde shortcut quality time if the topology is known in advance, but not the input. So basically, you can match this lower bound on each graph G if you know the topologies in advance, which is somewhat unfortunate. However, you don't need this assumption of knowing the topology in advance on special types of graphs, such as minor free graphs or expanders. And we also conjecture this is true in general for you know, like on all graphs without any restrictions. And there is some extremely interesting progress being done on this front. There is some very interesting progress there. So yeah, I kind of changed the model on you on the upper bound, in the sense that I require you to know the topology, meaning so every node needs to know how the entire graph looks like, but it does not need to know the input. This is equivalent to saying, okay, I give you polynomial preprocessing time before I give you the input. That's equivalent. Or this is even equivalent to saying I will give you many polynomial many problems that you need to solve in succession, and you are allowed to amortize the cost of solving by doing some by learning the graph in the beginning. But however, you can kind of even forget this, because I believe this will be relieved in very short-term future. Okay, so if you follow along, you could see that for every graph G, we have a lower bound of shortcut quality for the distributed MST, and we have an upper bound of the shortcut quality. So the combining together, that actually means that we have universally optimal algorithms for the distributed MST. Well, with an asterisk, when the topology is known on the special graphs, but we ignore that. Perfect. So this is actually a very strong result, in my opinion at least, and it is achieved using the low congestion shortcut framework. Now, the same framework gives universally optimal algorithms for other distributed problems, such as approximate distributed shortest path, or approximate distributed min cut, distributed connectivity verification, and so on. Moreover, shortcut quality as a parameter characterizes all of these problems that I just said, which is not something that you would expect, because it could very well be the case that each one of these problems would have their own parameter that would characterize them. But it just so turns out that all of these problems are actually characterized by the same parameter, shortcut quality. So actually, when you look at this in a little bit more detail, you can say that these problems interreduce to each other, and they form a newly observed complexity class of distributed global algorithms that all interreduce to each other. So if you can solve any one of them, you can solve all of them. And they are actually characterized by the shortcut quality of the graph. And in this, minimum spanning tree, shortest path, min cut, many very important and interesting problems fall within this category, fall within this new complexity class. All right, so hopefully I managed to convince you that universal optimality is a useful concept that goes beyond the existential optimality currently prevalent in the literature. And I thought that we can actually achieve it. Now we're gonna dive a little bit deeper into the framework that is able to achieve these results, so-called low congestion shortcut framework. I'm gonna define shortcuts, what they are, and then I'm gonna give two applications of them, how to use them. And finally, I'm gonna tell you how you can use the framework for yourself tomorrow without knowing any of the underlying detail, and actually construct universally optimal algorithms for yourself. All right, so let's start. All right, so the most important definition is what are shortcuts and what is that shortcut quality parameter that I was talking about. So you have an undirected graph G, and in that graph G, an adversary gives you connected node disjoint parts P1 to Pk. All right, so you're given P. So let's actually draw this. Just a moment. So in a graph, you're given different parts. So let's say this is one part, this is another part, and you know these are some node disjoint part. They're you can imagine that all of these parts want to communicate something in themselves. I don't know, find out the sum of all the nodes inside each one of those parts. All right, so now we define a shortcut of quality Q for this set of parts P1 and P2. And how do we do this? Well, first off, each one of those parts wants to communicate a little bit faster among themselves. So they could use only internal edges because they are connected, but that would take a lot of time because each one of those parts would have a huge diameter, much bigger than the diameter of the entire graph. So because of this, we're going to augment each one of these parts Pi with an additional set of edges Fi. And we are going to do it in such a way that the diameter of that part plus the additional edges is at most Q, the shortcut quality. All right? And all right, so basically let's do this again. So let's say we have a part. So we're going to add extra edges to this part P1. We're going to add these edges F1 such that P1 plus F1 has a small diameter, has a diameter of at most Q. However, we don't want to give every edge to everyone because that would cause congestion issues. So we want to balance out the diameter of each one of those parts with the congestion. So, and we say that the congestion is such that, so we want each edge E to be used by at most Q different parts F. And so we say that the congestion is at most Q if every edge E is used by at most Q different parts F. When all of these conditions are met, we say we have a shortcut of quality Q for this set of parts Pi. So imagine it this way, you give me a set of parts P1 to Pk, and I will find a shortcut of quality Q, meaning I will find F1 to Fk, such that the diameter is small and I don't use any of the edges too many times. Alright, so this is a shortcut quality with respect to the parts. And now the shortcut quality of a graph is just the worst case set of parts connected and not disjoint. And now you find me the best shortcut quality for this set of parts. So the shortcut quality of a graph G is just the worst case possible shortcut quality over any set of parts that is connected and not disjoint. Alright, so now why is this even a useful definition? One thing that we're going to look at is the problem, that so-called part aggregation problem, which is more or less that motivated this entire definition. So the thing is here, we are given connected node disjoint parts P1 to Pk as we had before. Each node has some private input xv, and each part needs to learn the minimum of the inputs in its parts. So basically, as we had before, we have a graph and we have some parts, and each node has some input, and we want the entire part to know the minimum xv for xv in that part. And we want every part to do this simultaneously in parallel. Alright. Now, if you give me a shortcut of quality Q, you can actually solve this in Q rounds in the usual congest model, obviously. So let me tell you why. So imagine that you're given, there is only one part, P1. Now you can kind of see that because we added these extra edges in, whatever, so imagine there is only one part, because we added this extra edges in, just by communicating over the Pi and the edges, well, the diameter is at most Q, so therefore you can do a BFS among them and just find out the minimum, always find the minimum, propagate the minimum, do the natural thing, and actually after Q many rounds it will actually solve the problem. Now, do keep in mind that there are multiple parts inside, and you need to also take care of congestion issues, so like, you know, some edge could could also be in some other parts, and that is actually fine. If you're careful along it, you should use like some well-known randomized delay strategies, and you can definitely deal with it. And if there is a shortcut of quality Q, you can actually do this in Q many rounds. Now, if you don't believe me, I'll add some hints here. You don't need to read it now, but you can pause the video and read it if you want to know how is this actually done. All right. Now, let me actually tell you a little bit more, a little bit less artificial example. So what if you want to solve the minimum spanning tree? If you know how to construct good shortcuts. All right. So now, let me define a shortcut construction oracle. So suppose that for every each set of connected node disjoint parts, there is an oracle that will construct you a shortcut of quality Q for that set of parts. So you give the oracle the set of parts in some distributed way, and the oracle spits out, outputs a shortcut of quality Q in some distributed way for that set of parts. So now it's not that hard to see that actually if you are given a construction oracle of quality Q, you can solve the minimum spanning tree problem in Q many rounds. And the analysis for this is you just run the most standard Boruvka algorithm. So the standard Boruvka MST algorithm, you probably remember, but let's review it a little bit. How does it work? Well, you can imagine that in the beginning, each node V finds the minimum outgoing edge around it. So, all right. Now you add that edge to the minimum spanning tree. So every node V adds that edge to the minimum spanning tree, and then you contract the edge. And repeat log n times. After the log n times, everything will shrink down, contract to a single component, and all the edges that you add will form the minimum spanning tree. Well, how do you use the oracle here? Well, once you start, when you start an edge, and then you add another, and then later, each one of the nodes will grow into some component. These components will be node disjoint and connected, because that's how they made. So, and the only thing you need to do in the inner loop is to find the minimum outgoing edge, which is exactly the problem that we solved like a few slides before. This is find the minimum outgoing edge in the component. So that's exactly what we're going to do here. We just call the parties aggregation oracle to find the minimum outgoing edge. We just solve the parties aggregation problem using the construction oracle and find the minimum outgoing edge in each one of those components, and that is it. This is basically all the things you need to do to solve the minimum spanning tree. And it is, up to some details you need to take care of. It kind of is that simple if you have access to this shortcut construction oracle. All right, so now how would you use this framework for yourself? Now I kind of told you, given this construction oracle, which is part of the framework, how do you actually use this for yourself? So suppose you're given a distributed global problem pi, so I don't know, like the minimum spanning tree or the distributed maximum flow and the other problem. The first question you want to ask yourself for the upper bound is, can you solve pi using polylogarithmic many calls to the parties aggregation? So can you solve it with polylogarithmic many parties aggregation calls? The way I intuitively think about it is that the parties aggregation allows you to contract subgraphs and operate on minors appears. So as you saw in the Boruvka example, you could contract, you can take an edge, you can take a node, take an edge adjacent to it and contract it, and you're still able to operate on this. This is like a good way of thinking about this. If the answer is yes, then you can actually solve the problem pi in O tilde shortcut quality time. All right. Why? Well, the only thing, how does it work? So you take your algorithm pi, you decompose it in polylog many parties aggregation. Now the framework, I never really told you this, but the framework that we actually do is it actually constructs shortcuts of shortcut quality time. It does it with an asterisk. This is where the asterisk comes from, because it does it like generally only if you know the topology, but also we also know how to do it on special graph classes like minor, free, planar, expanders, and so on. With various loss factors there. But the framework provides you a way to actually construct shortcuts and therefore solve the partial segregation problem. You don't even need to know the details of it, you can just cite that. That's for the upper bound. Now for the lower bound, the question you'd want to ask yourself, is your problem harder than distributed connectivity? So does it reduce to connectivity? So if it asks anything like, oh, are two nodes connected, or is the subgraph connected, or anything like that, typically it is. And shortest path and minimum cut and maximum flow and all these problems like that do reduce the connectivity. And, or connectivity is harder than them. Oh, sorry, connectivity is an easier problem than them. They are harder than connectivity. And if this is the case, then your problem requires omega tilde shortcut quality time. And clearly both of them are true, you have a universally optimal algorithm, and that algorithm requires exactly shortcut quality time up to polylogarithmic factors. Okay, so if you have shortcut quality time you have a shortcut quality time algorithm. But the one thing that I never really told you is like, okay, shortcut quality, is that a big quantity or a large or a small quantity? Well, one thing that you maybe could have inferred if you're very carefully following is that shortcut quality is always less than d plus square root 10. Because you can solve MST in any graph in d plus square root 10, and this actually is the worst case. However, for many graph classes, shortcut quality is much smaller quantity. So for planar, genus bounded, treated bounded, minor free graphs, and so on, shortcut quality is diameter, O tilde of the diameter. So you cannot really ask for anything better than that, because diameter is like a trivial lower bound for every global problem that we talked about today. And very similarly for expanders, well, while we know that there is a polylog shortcut quality, we only know how to construct it in n to the little of one time. So basically, if you want to use the framework yourself, you only need to show how to solve the problem with partial segregation. Then you immediately get a shortcut quality time algorithm, and now you immediately know that for many graphs, this is actually extremely fast. All right, so this is the this is the end of the shortcut the local gesture shortcut technique, and now we're going to continue on the more high-level technical overview, and I'm going to discuss a little bit more in-depth proofs and how this entire thing works in details. Now, in order to do this, I will actually copy-paste a talk that I did previously for Stock 2021. Thank you and enjoy. I am now going to give a high-level technical overview of both the upper bound and the lower bound of the paper. So the claim is, for the upper bound, that if we can construct shortcuts efficiently, then we can solve the minimum spanning tree in shortcut quality time as we wanted. So the question is, can we actually construct shortcuts efficiently? We show in this paper that the answer is yes, but currently we only know how to do this in the known topology setting, and this is why we need the known topology assumption for the upper bound. The question, however, is far from easy, because you can think about it in the following way. The challenge is that different parts of the graph need to communicate internally amongst themselves without knowing what the other parts of the graph are. So one part needs to communicate without knowing what other demands for communication are in the graph. Well, you can actually learn a little bit about other parts, but not too much, because you need to be efficient, and during a small number of rounds you can only learn a small amount of information about other parts. You definitely cannot learn all about other demands and parts. So this is even a challenge in the known topology setting, because even though you know the entire topology, you do not know what other demands exist in a graph, what other parts of the graph want to communicate within themselves. So one way to go about it is to make the problem even harder. Let's say we don't want to learn, not only we say we can't learn much about it, let's learn nothing about it. Now, you want that every part of the graph that wants to communicate with itself is completely oblivious about the other parts of the graph, but you still want to be able to get near optimal solutions. This is so-called the oblivious routing problem that has been studied mostly in the literature. So we try to utilize this oblivious routing, and that's the way how we actually go about this. However, in our setting, we need to balance both between the diameter and congestion, whereas standard oblivious routing solutions only optimize for the congestion. So the problem with this is that standard solutions fails. We need to take into account both the diameter and the congestion and jointly optimize between them. This is a completely new problem for which the standard solutions don't really work. So we actually solved this problem in a separate paper called the Hopf-constrained oblivious routing. And in case you're interested in hearing more, check out the paper or the accompanying talk on YouTube. This paper is also set to appear in Stock 2021. So putting these things together, we have the following theorem for our upper bound. Suppose that all nodes know the topology of G up front, then we can construct shortcuts of near optimal quality Q in order Q many rounds. And consequently, we can also solve the minimum spanning tree in shortcut quality rounds. We now turn to the lower bound side of things. In order to prove the lower bound, that you cannot solve MST faster than shortcut quality time, we will first go through an intermediate problem called the distributed disjointness task. Alright, so what is this task? It is a two-player game between Alice and Bob. So you have Alice and you have Bob, and they are both given a k-bit input x and y. So Alice is given its own k-bit input, let's say 0, 0, 1, 0, and Bob is given its own k-bit input, let's say 0, 1, 1, 1. Now, this game is actually played on a graph. So we are given k node disjoint paths, p1 to pk, so paths in the graph. So let's say path number 1 looks something like this. We have path number 2, path number 3, and path number 4. There are no disjoint. And Alice controls the heads of these paths. So Alice controls, let's say, these nodes. These are the heads. Whereas Bob controls the tails of these paths. And by controls, I mean it can see all the stuff that the nodes receive, and it can also tell the nodes what to send in the following round. The question is, what is the minimum amount of rounds until both Alice and Bob can decide whether their inputs are disjoint or not? So we say that two bit strings are not disjoint if there exists such an input I, such an index I, between 1 and k, such that the ith bit of the Alice's input and the ith bit of Bob's input are both 1. So in this example, the third bit, this one, of Alice's input, and the third bit of Bob's input are 1, so they are not disjoint. The problem does not ask us to find a particular index, but it's simply a yes-no decision question, where both of them need to find out are they disjoint or not. How they do it, well, the particular index you don't really need to find, you just want to answer yes or no. Now, the theorem that we prove is that this distributed disjointness task is very intricately connected to the shortcut quality. Particularly, given a set of paths p1 to pk, if you can solve the distributed disjointness task on every subset of these paths in q rounds, then you can also find shortcut of quality q for this set of paths. And this is an if and only if condition. One side, that if there exist shortcuts of quality q, you can solve the distributed disjointness task, is relatively easy, and you can see this if you think about it. However, the other task is somewhat more surprising. Why? Because in order to say that you cannot solve a communication problem of distributed disjointness, if there does not exist these combinatorial objects of shortcuts, seems to be a hard thing to prove. Because, yeah, you're bounding a communication problem via a combinatorial property. However, this kind of results are known in network theory, network holding theory, and information theory, and they are called network holding gaps. And because of this, we proved such a network holding gap for this problem in a separate paper called Network Holding Gaps for Completion Times of Multiple Unicasts. It's a joint work by Bernard Holper and David Weitz that appeared in Fox 2020, and a talk is available on YouTube. And I would advise you, if you would like to know more how you actually prove this network holding gaps, how do you bound a communication test by a combinatorial property, I would advise you to see the talk or the paper. Alright, so we go through this distributed disjointness task as an intermediary. Okay, now let's talk, when we have all the ingredients in place, let's give a high-level overview of how this proof actually looks like. What we would like to prove, one more time, for the lower bound, is that the time to solve the minimum spanning tree problem is up to polylogs more than the shortcut quality of G. Now, how do we actually prove this? Suppose that there is a very fast MST algorithm that works in Q time. First, we show a reduction that using the MST oracle, we can solve the distributed disjointness problem. Furthermore, using the network holding gap from the previous slide, we then argue that if there is a good solution to the distributed disjointness problem, there is a good shortcut quality. So this is actually how the lower bound works in its entirety. I will now give a more in-depth overview about how the lower bound actually works. So the statement that we would like to prove is we want to show that the time to solve the minimum spanning tree on any graph G is lower bounded by the shortcut quality of G up to polylog factors. Now, equivalently, we can state it in the following way. So, given any set of connected and non-disjoint parts, P1 to Pk, we can construct shortcuts of quality order TMST on them. Alright, because that's kind of the question. If you construct on any set of parts a shortcut of quality TMST, then assuming that TMST is small, you get small shortcut quality. Perfect. The first idea that I would like to observe is that we can actually assume that the parts are not general node subsets, but they're only paths, like SITI paths, which have a much simpler structure. So we state the theorem in the following equivalent way. Given any set of node-adjoint paths, P1 to Pk, we construct TMST shortcuts on them. Alright, so the question why this holds, I'm not going to go much deeper in it, but the idea is to use a heavy light decomposition and then just apply the path theorem to construct general shortcuts on any general parts. If you'd like to know the details, I actually put some hint on the next slide. So feel free to stop here and see how it actually works if you're interested in it. Moving forward, the question is how do we actually prove it? How do we construct TMST shortcuts on a set of paths? The thing that helps us here is the following definition of a disjointness gadget. Okay, so the definition says a disjointness gadget of a set of node-disjoint paths P1 to Pk. So here it's going to be, we have this set of paths P1 to Pk. Is a connected subset of edges, denoted here in blue, that touches every head and every tail of all of those paths, so head and every tail of all of those paths, but does not otherwise intersect the interior. So F does not intersect like the interior of those paths. Perfect. Now this is not really the full definition, it has one exception, that you're also allowing constant many exception intervals of small order D length on each one of those paths, and I will allow you to intersect F inside of these exceptions. However, for now, it might be a little bit conceptually easier if you just ignore this for now and just imagine that it does not intersect the interior. Handling these exceptional intervals is relatively straightforward. Okay, so now the question is how do we use these disjointness gadgets? The observation here is that if you have a disjointness gadget on a set of non-disjoint paths, then using a single call to the MST oracle, you can solve the distributed disjointness task on P. Alright, so why does this observation work? What's the idea? Well, assume assume you want to solve the distributed disjointness task. So Alice and Bob get inputs X and Y. I'm going to tell you how do you assign the minimum spanning tree costs such that when you call the minimum spanning tree oracle, you get a cost of 0 if and only if X and Y are disjoint. Alright, so that's kind of what we're trying to do. So this is what we're going to do here. First off, to all the edges in F, so all the blue edges, you are going to assign a cost of 0. Okay, so all the edges in F, you're going to assign a cost of 0. Furthermore, look at every one of the paths, P1, P2, and so on. And now, in each one of them, to all the edges except the first edge and the last edge, you're also going to assign a cost of 0. Alright, same thing on the other paths. All 0, all 0, all 0. And finally, on the first edge on each of the paths and the last edge of each of the paths, you're going to assign the Alice's and Bob's inputs. So for instance, on the first edge of the path, you're going to assign the Alice's input x1, x2, and so on, up to xk. And on the last, it's going to be similar, y1 to yk. Now, the idea is, if there is an MST of cost 0, then it cannot happen that any one of those paths, for instance this one, it cannot have a cost of the first and the last edge of 1. So if this is a 1 and this is a 1, the MST cost cannot be 0. It must be more than 0. So if the MST cost of 0, each path has at least one xi or yi to be 0, and therefore they must be disjoint. And similarly, it has a cost of more than 1, there must be at least one path that have a common 1, and therefore they're not disjoint. So that's it. That's the entire idea. So if you can find disjointness gadgets, you can solve the distributed disjointness task on those set of paths. So now the big question is, how do you actually construct the disjointness gadgets? And this is actually where the main technical contribution of the paper is, because given a set of no disjoint paths P, I claim that there exists a disjointness gadget of large size, with large size means the size is 1 over a polylog factor of the original set of paths. However, finding it is fairly technically involved. Now, suppose that we assume we know how to find them. Let's see how do we complete the proof. Well, it's fairly straightforward and conceptual, so let's go through with it. So, assume the theorem. So, our task is to construct shortcuts of quality TMST on an arbitrary set of no disjoint paths P. What do? We find a large disjointness gadget on a large subset P prime of 1 over polylog fraction. Because this is a disjointness gadget, using the theorem from the observation from the last slide, we can solve the distributed disjointness task on this set of paths P prime in T order T MST time. Using the network coding gap result, we now know that there actually exists good shortcuts on P prime of quality T MST. And finally, we have the good shortcuts on this P prime. We remove P prime from P and remember the shortcuts and repeat this polylog many times, each time finding a shortcut for a 1 over polylog fraction of the paths, finding the shortcut, remembering it, removing that, and repeating. Since in the end you kind of take the union of all the shortcuts you ever find, I claim the quality of the final shortcut it only increased by a polylog factor, so it will have a quality of order TMST. So that is it, that's the entire proof. Alright, after you have internalized the rest of the proof, the main thing that is remaining is how to actually construct these disjointness gadgets. So, as I said before, constructing the large disjointness gadgets, such that when you're given a set of no disjoint paths P, you want to find a disjointness gadget on a 1 over polylog fraction, that's hard and technically involved. However, I can show you now some intuition about how to get a little bit weaker result, the one where you get 1 over an order D fraction of the paths. So here is how it goes. Suppose that you have those set of original no disjoint paths P here on the down left, and the procedure is like this. First, what you do is you choose an arbitrary root R. So just choose an arbitrary node, let's put it here, and call it the root R. So now, let's consider what would have happened if we add some path pi to our set of disjoint gadget paths p prime. So let's say that this is our path pi, and what do? We take a walk from the head and the tail to the root via some shortest path of length at most order d. You can clearly find such a thing because the diameter of the graph is d. So we come and you take a walk towards the root. So it does something like this, and then it intersects possibly some other paths, and eventually it reaches the root. And clearly you kind of do the same thing from the rest, from the tail. Okay, so what do? We add these two walks to f, which, good, that makes sense. We add this to f because, yeah, we want to have this f to be a one connected component. So since it's connected to, all of them are connected to this root r, they're going to form one connected component if we can actually do this properly without intersecting the interiors. Okay, so this walks that we want to add to f intersect some other paths. So what do? We would just delete them. So in this example here, well, we would just say, well, let's delete this one, first one, and the second path. And we will not deal with them in the first, in the call. We will just delete them and deal with them sometimes later. All right. Now, the last thing that is a little bit of a problem is that these two walks that we started from a path pi might intersect the path pi itself. Now, we do have a little bit of leeway. If you remember, we can actually have a constant number of so-called exceptional intervals on each one of those paths. And if those intervals are of small length, at most order d, we can allow this f to intersect those exceptional intervals. Now, so clearly what you want to do is you want to say, well, since in the beginning and in the end the walks can intersect the path, you want to say, well, let's pronounce this an exceptional interval. And this is completely fine, but it might happen that the exceptional interval done in this way might be too long, because we actually at the end want that the exceptional intervals have a length of at most d. Right? So let's say, so if they have a length of at most d, then you pronounce them exceptional intervals and you're complete, and you would be done with this. However, it could happen that this is obviously not the case, and in this case we do a little bit of switching. So what does that mean? It could just so happen that there is a very short path, like order d, right? But it kind of intersects, so this is at most d, but it doesn't, but the thing that we want to pronounce the exceptional interval has a length of much, much, much more than d. In this case, well, there is a very simple solution. We can just switch it around. We can say, well, take the last intersection of your walk from the head to the root with the path and pronounce that part as the actual new version of the path. So we'll have a new version of the path that goes like this, and this part you would completely discard. And now you actually can pronounce this an exceptional interval because it has a length of at most d. So after the switching, you can pronounce it an exceptional interval, and now you can actually connect to the path and you can actually connect to the path. Okay, so this actually kind of ends the story on what would have happened if we were add to pi to the set of disjointed gadget paths p prime. Now we never really actually did it because those paths could delete each other that we would choose. But there is a very simple argument that you can actually choose some subset of them that do not delete each other. The main step here is to just see that every path pi deletes only order d many other paths. Well, this is clear because those walks have only order d length. So, and each hop of the walk deletes at most one or two other paths. So clearly it's going to be at most order d. So what do? You can make a very simple argument that you can find an independent set p prime of paths that is at most a size 1 over order d of the original set of paths that do not delete each other. So that is the complete proof. This is kind of how you fix the construction up to an order d factor. So now let us conclude and give some open questions. nothing like this was known before, as in the only universal lower bound that was known before was the trivial diameter one. So here we showed that shortcut quality is a universal lower bound. And we also show that it can actually be matched. So there exists algorithms that work in O of tilde of shortcut quality time, which actually gives the first universally optimal algorithms, but currently only when the topology is known. Now the obvious natural conjecture is to prove that actually you can do this on every graph, and for this you actually only need to show that shortcuts can be constructed efficiently, or near optimal shortcuts for quality Q can be constructed in order Q time up to polylogs. This would actually give a characterization for every topology, so in the usual congest model where you do not know the topology, and would give universally optimal algorithms in every graph. Now, there are many connections of this work to other fields of theoretical computer science, because it's kind of a new result, and to work upon it, we needed to develop tools from many different areas of TCS. So to give a few examples, these include new network coding gaps from information theory. These include new types of oblivious routings from like graph theory and approximation algorithms. And also these include new connections between distributed computing and communication complexity. And now the nice thing here is that not only do we draw from these areas to prove our result, but the line of question is asked in this paper kind of influenced new results in those other areas, and now there is kind of a mutual benefit, because the questions lined in this line of work benefited the other areas because we were able to solve some questions there that were, I would say, notable and nice. All right, so the open questions remaining, well, we can pose a bunch of them, and they're kind of natural. Are there universal optimal algorithms in other models? So, for instance, what about when you worry not about the time, but about communication complexity? Or you worry about both time and communication complexity jointly. Can you have both? Can you be, universally optimal in both? And what would that even mean? Or maybe you want to be just with respect to time in the congest broadcast model, or in the radio model, or some other model. So that is kind of a way, develop universal optimality in other models. And the other question that I like to pose is also a very natural one. Can you have universally optimal algorithms for other problems? So here we show that it works for distributed minimum spanning tree and approximate shortest path and approximate min cut and so on. But for instance, we do not know anything about exact min cut or exact shortest path or any other problem that comes to mind, all pair shortest path, which I don't believe even the shortcut quality is the right answer, but it should be something completely else. All right, so that will be it, and thank you for your attention.